Welcome to the 2021 Isaac Newton Institute contribution to the Cambridge Festival, formerly known as the Cambridge Science Festival. And I am over the moon to have our speaker for today. Emily Shuckburgh is just such an inspiration and role model to so many. So Emily, she is director of Cambridge Zero, which is the university's major climate change initiative. And she's also a reader in the environmental data science department of the Department of Computer Science and Technology. And she leads the UKRA Centre for Doctor Training on the application of AI to the study of environmental risks. Emily is a mathematician, a brilliant mathematician and climate scientist, and she's a fellow of Darwin College, also a fellow of the Cambridge Institute for Sustainability Leadership, an associate fellow for the Centre of Science and Policy. She is a fellow of the British Antarctic Survey, where she had formerly been deputy director. She is a fellow of the Royal Meteorological Society. And in 2016, she was awarded an OBE for her services to science and the public communication of science. So it is absolutely such a privilege that we have Emily today. And more than that, our special closeness to Emily ourselves at the Newton Institute is she was a really helpful member of our scientific steering committee, which is the scientific body that helps advise on which programs we should or should not run at the Newton Institute. And another little nugget of information I'm going to tell you about Emily is that she's actually co-author amongst numerous luminary academic papers. She's also co-author of the Ladybird book on climate change. So perhaps if you don't want to read many of her academic papers, maybe that might be one that some of you might want to go for. Anyway, as I say, it gives me such great pleasure to welcome you here today, Emily. In fact, I've come into the Institute especially for this occasion, although sadly the building is at present empty, but it will be reopening its doors again soon. And so without any further ado, Emily, thank you so much for doing this for us, and I hand over to you.
Thank you very much, Christy, and it's a real shame to actually not be physically in the Newton Institute today delivering this talk, but hopefully we will be back to in-person events soon. So what I'm going to do today is I'm going to give a bit of a description about how mathematics can be used both to help understand our changing climate and also to help shape some of the solutions to climate change. So let me just share my screen so you can see my presentation. There we go. So mathematics, a toolkit to tackle climate change. I thought I'd start off just by kind of setting the scene in terms of, if you like, this provides a dashboard of how our climate has been changing or how our world has been changing over the last 150 years. And what you can see here is just 4 data sets that describe that changing world. Carbon dioxide levels in the atmosphere, you can see, well, actually you can see pretty much all of these graphs on here show close to exponential increases. There've been this dramatic increase in the amount of carbon dioxide in the atmosphere, 50% increase over that 150 years. And the next graph that you see on this dashboard across shows how global society has changed over the last 150 years. Huge increase in the industrialization of many countries, and that industrialization has up until now been driven primarily by the use of fossil fuels for energy, which has contributed to that carbon dioxide increase. We've also completely changed our landscape, significant deforestation around the world, again contributing to that increase in carbon dioxide levels. And of course, other human activities have also contributed to an increase in other greenhouse gases in the atmosphere too, the increase in industrialized agriculture, for example. That has then led to a change in our climate. If you increase the amount of greenhouse gases in the atmosphere, you would expect an increase in the temperature of the Earth, and that is indeed what we've seen, over 1 degree Celsius increase over the last 150 years. And as the temperature of the atmosphere has warmed up, that's had a knock-on effect on other aspects of the climate system as well. And there's just one other data set that I've got here, which is sea level rise. We've seen about 25 centimeters of sea level rise over this time period. And that sea level rise has come about principally through two causes. The first is that the oceans have slowly been warming up, and as the water in the oceans warms, the volume of water in the oceans has increased, and that's contributed to sea level rise. But in addition, we've been seeing melting of ice around the world, and where that ice is sat on land, when it melts, it finds its way into the oceans, and that has also been raising sea levels. So, you know, the real world impacts of these are seen in terms of, you know, extreme weather events that are occurring around the world as temperatures are reaching extreme levels. We can observe the loss of ice from the polar regions, from Greenland and Antarctica, which is contributing, as I already described, that accelerating sea level rise. But there are other implications as well in terms of that increased carbon dioxide. It's not simply climate change, it's also that we're seeing a significant acidification of the oceans as that carbon dioxide finds its way into the oceans. And that's just one example where that carbon dioxide pollution, if you like, is contributing to significant damage to ecosystems as well as to these physical changes to the natural world. And in terms of extreme weather events, we're seeing an increased risk of extreme weather events occurring around the world as a consequence of climate change. 2 summers ago, we saw 2019, we saw record temperatures in Cambridge, the record for the UK, 38.7 degrees, recorded in the Botanic Gardens. But we've also seen repeated episodes of flooding in this country, causing absolute devastation to communities around the country. But if we look globally, the map that you see in the background of this slide is a compilation of extreme weather events globally around the world that have occurred, where after they've occurred, there's been careful scientific analysis to ask, has the risk of those extreme weather events occurring increased as a consequence of the climate change we've already seen to date? In the example of heat waves, I think it's probably pretty obvious that if you increase temperatures on average, then you increase the risk of heat waves. For these flooding events, it's possibly not quite so obvious what the connection is, but broadly, physics tells you that a warmer atmosphere is a wetter atmosphere, holds more water vapor, and so there's more water in the atmosphere to rain down in heavy rainfall events, and that's what results in an increased risk of flooding in certain parts of the world. So all the instances that you see coloured in red dots on the slide and background show instances where the scientific analysis has indicated an increase in risk of those extreme weather events occurring as a consequence of climate change. So that's how our climate is changing. Where is the role of mathematical science in terms of contributing to our understanding and the solutions? And there's 2 things that I want to talk about today. First of all, I want to talk about the role of mathematical science in helping us assess and monitor the risks associated with climate change. And then I want to talk about how mathematical science can help contribute to sustainable solutions to climate change. But let's first think about how mathematics helps our understanding of climate risk and our ability to understand what the future evolution of climate might be. So let's start off 200 years ago. Joseph Fourier, very famous mathematician, wrote a paper where he said in the paper that he hoped that geometers would not only go on in their researches into the questions of calculus, but they would consider the question of terrestrial temperature, which he said was one of the most important and most difficult questions in all of natural philosophy. And what I wanted to do was to give you a sense of how, from that starting point, we, over the course of the last 200 years, have steadily developed in more sophisticated ways our ability to model our climate. So I thought I'd start off here with this. There's only two sets of equations I'm going to show you today, but this is one of them, and I'm showing it to you because I think it's a really nice example as to how mathematics can help provide really valuable insight and also predictive power into some of these questions. So it's possible, I'm not going to show you how to derive it, but it's very straightforward to derive a very simple model of what our climate is, and to write it down in terms of the equation that I've shown here. And so this is looking at exactly that question that Fourier was asking. What determines the temperature of the surface of the Earth? So TG here is the temperature of the ground. By developing a very simple model of the climate that simply has the amount of energy coming in from the sun, which is F, the fact that some of that energy coming in from the sun is immediately reflected back to space, and that's what's known as the albedo of the Earth. So where we have a lot of ice in the polar regions, for example, that reflects a lot of that energy straight back to space. And it turns out that about 30% of the energy coming in from the sun is reflected straight back. And so that's the alpha in this equation here, around about 0.3. You can assume in this really simple model that the Earth itself radiates like a black body, and there's a law from physics that tells you how that black body radiation works, and it goes with the fourth power of the temperature. And there's a constant that is within that called the Stefan-Boltzmann constant, which is the sigma that I showed there. And then the only other thing that you need in this very simple model of what the climate is the atmosphere. And the key thing about the atmosphere in terms of this really simple model is that the atmosphere transmits through it a larger fraction of the shortwave radiation coming in from the sun than of the long wave radiation going back out to space. That's essentially the greenhouse effect. So if you put in that differential fraction of shortwave versus long wave radiation, then that's the final thing that you need to complete this balance between the incoming radiation from the sun, the outgoing radiation from the Earth, creates this equation and gives you all the variables that tell you how the temperature of the surface of the Earth is determined in this very simple model. And in fact, if you put in reasonable numbers for each of these different variables in there, then you indeed are able to replicate approximately the temperature of the surface of the Earth. But this equation is much more powerful than that. It doesn't just give you a prediction of the temperature, but it also tells you how that temperature might vary if you varied some of these parameters. So let's have a look at that. So if you imagine that for some reason, for example, over really long time periods, the orbit of the Earth around the sun varies, and sometimes where the Earth is a bit further away from the sun and sometimes it's a bit closer to the sun. And if that happens, then the solar flux, F in this equation, would decrease. And you can just see, you know, if you go up and look at this equation, what would happen if F decreases? Well, temperature would go down. So if the solar flux decreases, the temperature decreases. So if the orbit we're in an orbit slightly further away, the temperature would decrease. Now, if the temperature decreases, you would likely see an expansion of the polar ice caps, for example, and that would mean that the albedo, the amount of sunlight that's immediately reflected from the Earth, would increase. So you would expect alpha to increase. And again, if we go back and look at this formula, what would happen if alpha increases? Well, there's a minus sign in this formula in front of the alpha. So if alpha increases, then you would expect the temperature to decrease still further. And what then happens as the temperature decreases still further? Well, one resulting factor is that you can end up having less carbon dioxide in the atmosphere, and in part that is because there's large stores of carbon dioxide in the oceans. As you increase the ice sheets over the oceans, then that traps that carbon dioxide in the oceans less is able to escape out into the atmosphere. Or similarly with the land, you'll have more ice cover over the land, and that will also change the way in which the carbon dioxide exchanges with the atmosphere. So you can have less carbon dioxide, and that would result in a change in that transmission of long wave radiation, and decrease the temperature still further. And essentially it's that set of mechanisms that lead to an ice age, triggered originally by the change in the orbit of the Earth around the Sun. Now we can see whether or not that sort of chain of events actually happens in Earth's history if we go to Antarctica and look at the ice cores that you can drill into the Antarctic ice. And this is a photograph of a slice through an ice core, and you can see that there are tiny bubbles of air that are trapped in that ice. And through drilling down deep into the ice, we're able to recover air that was in the atmosphere well, up to 1 million years ago in the past. So we're able to determine what the actual atmosphere was like 1 million years ago. And this is the actual data from some ice cores. And you can see that the bottom curve here is the amount of carbon dioxide in the atmosphere. The top curve is the temperature, and both vary in sync with each other, but also in sync with the changes in the orbit of the Earth about the Sun over these really, really long time periods. And you can, that simple formula that we derived for how these changes occur are very much matched with, at least in broad terms, with these changes that we see over time. But what has been happening more recently is that we've seen a really huge increase in the amount of carbon dioxide. So there is this natural cycle of change driven by the change in the orbit of the Earth about the Sun over these incredibly long time periods. And then over an incredibly short time period, we've seen a massive increase in the amount of carbon dioxide in the atmosphere, vastly exceeding that natural cycle of change brought about because, as I said at the start, we've been burning fossil fuels, cutting down trees and so forth. And so according to our formula, you increase that carbon dioxide in the atmosphere, you change the transmission of long wave radiation, and you'd expect an increase in the temperature of the surface of the Earth. So there's a very simple way in which mathematics can describe in very basic terms some of the key aspects of climate change. But how do we develop more sophisticated models of our climate that would also start to explain some of the changes in extreme weather events, for example, that I discussed at the start? Well, if we're going to develop a more sophisticated understanding of the atmosphere, and oceans and climate more generally, we need to have a more sophisticated model of our climate system. And one of the key things about our weather and climate is that both the atmosphere and the oceans, in terms of their physics, are essentially fluids sitting on a rotating sphere. And there's something very interesting about the dynamics, the way in which a fluid on a rotating sphere moves and its properties. And what I'm showing you here, well, first of all, the first image that you see here is a satellite picture. You can see the clouds swirling around in the atmosphere. It's a photograph taken from space. The next two pictures that you see here are laboratory experiments. And these laboratory experiments, you're looking down on a tank of water, and some coloured dye has been injected into that tank of water. And the difference between these two tanks is that on the left-hand side, the tank of water is just sat still on a table, and that green dye has been injected in and the red dye has been injected in, and it's just diffusing out as you would expect. On the right-hand side, what's the difference is that tank is rotating just as the Earth is rotating. And as soon as you start rotating a tank of water, you can see that you emerging out of these rather beautiful swirling patterns that actually are rather reminiscent of exactly the sort of swirling patterns that we see in those satellite pictures in terms of our clouds. And that is essentially because the dynamics that is the most important aspect of determining our the evolution of our atmosphere and our oceans is the fact that these are fluids on a rotating sphere. So we can actually use that to develop a model of how our atmosphere and oceans evolve. And the key aspects of that are that we have the motion governed by Newton's second law, that it's rotating and that we're sat on a sphere. And if we put those equations together, then we get a set of equations that are at the heart of all models of the weather and climate. And again, if we start looking, I put them here, the equations there, if you're interested. And if we look at them, you start to really learn some really important aspects of our weather and climate. And in particular, one key aspect of our weather is that one of the dominant balances is between the winds and the gradient in pressure. And so if we look at pressure maps that you sometimes see in weather forecasts, the wind circles around the pressure contours and is dependent in strength on the gradient between the high and the low pressure system. So when you see these very tight contours of pressure around a very low pressure point, then that's when you would expect to have the strongest winds. So you're immediately able to determine from this model aspects of our weather. Now this was then used, so we started off 200 years ago with Fourier, interested in the temperature of the surface of the Earth, and over the next, move forward 100 years to the beginning of the 20th century, and that was when the first weather forecasts were starting to be produced. And actually a Cambridge person, A.L.F. Richardson, produced the first numerical weather forecast, produced it using a slide rule, made a 6-hour forecast of pressure and wind, using much the same formulas as I've got at the top of this slide. Allegedly it took at least 6 months to produce and was very inaccurate, but set us on a course for developing weather and climate forecasts as we know them today. He wrote a very seminal book in 1922. We're nearly at the 100-year anniversary of it. And it really is an amazing book to read. And I've just got some quotes from it here. It says, imagine a large hall like a theatre, and the walls of this chamber are painted to form a map of the globe. And a myriad of computers are at work upon the weather. 64,000 human computers would be needed to race the weather for the whole globe. So he imagined having this vast amphitheatre filled with people all doing calculations as he was doing with his slide rule to try and project the future weather around the world. Well, roll forward to the 1950s, and exactly that was then being undertaken with by then what were the first real computers, and the first successful numerical projection of weather was produced in 1950. By that stage we moved on to punch cards from slide rules, and again it was nothing like as fast as the sort of weather projections that are produced today. It took 24 hours to produce a 24-hour forecast. So where are we today in terms of our ability to predict the weather and climate? Well, much those same initial ideas have been developed and developed and developed, and but at the heart of all weather and climate models is still that basic understanding of how our ability to write down the equations that determine the evolution of the atmosphere and ocean and the other key components of the climate system, and the way that we we produce numerical forecasts is to solve those equations on a grid. And you can see a schematic here showing the sorts of grid that is represented as an atmospheric component of a climate model. And the key thing here is that means, because we're solving the equations on a grid, it means that there's a whole set of processes that occur on scales that are smaller than that grid, that have to be parameterized, that have to be, we can't explicitly resolve them in terms of our numerical models. And that leads to uncertainty in terms of the final projections that come out. Now, the latest computers that are used to run these numerical projections of the weather and climate are really vast. The current UK Met Office, in terms of its weather projections, takes in over 200 billion weather observations from around the world every day, which it uses as a starting point for running the atmospheric model used for weather projections, which in itself has more than 1 million lines of code. It's very much the same model that is used for climate projections, but when we're interested in looking at the climate, it's not just the atmosphere that's important to consider the evolution of, but also the ocean, not just the surface ocean, but all the way down at depth, the evolution of the land surface, the ice of the world, and increasingly the chemistry of the atmosphere and the aspects of biological aspects in terms of the land and the oceans as well. The models are getting increasingly complex in terms of the number of components that are included. And so climate models now are able to provide projections of future climate. And there's a vast coordinated international effort known as the Climate Model Intercomparison Project, where some 24 or so slightly different climate models from around the world are all run in a coordinated effort to produce future projections of climate change. And those feed into the reports of the Intergovernmental Panel on Climate Change. And you can see here from the last Intergovernmental Panel on Climate Change report, the projections of future climate in terms of the global average surface temperature under a high emissions and a low emissions scenario. Now, that shows global average temperature. If we're interested in understanding the risk of extreme weather events, as I was describing at the start, then we need to understand what's happening at a local level. And that's much more challenging from a prediction perspective. So what I'm showing here is some of those 24 different climate models that are from around the world. And they're the actual maps of the temperature change that each of them predicts. And what you can see is that although they all these predictions, this is looking at the end of the century under one particular scenario, they're all showing warming, but in terms of the detail at a regional local level, they're all quite different. And this is a real challenge in terms of understanding at a local level the risk of extreme events into the future, and one that we're undertaking a lot of research now to try to improve our ability to quantify. But again, mathematics is absolutely at the heart of our ability to improve those projections. So in terms of how we can start to push the boundaries still further in terms of our ability to improve our projections, one thing that there's a huge interest in is whether or not we can adopt not just physics-based modelling of our future climate, but inject data-driven modelling as well. And we have vast data sets now for how our world is changing, coming from satellite observations, coming from networks of sensors. This is a map showing all the ocean floats that are that are taking observations not just at the surface but down into the depths of the oceans, sending back their data via satellite. And there's a huge resource in terms of describing the current state of the oceans. We also increasingly have other sources of data. This is a project that's been looking, a citizen science project that's been looking at transcribing old ship's logs to push back even further back into time the records that we have of weather conditions. So how can we make better use of these great data sets of how our weather has changed in the past? And can we use new machine learning and AI techniques in order to be able to make better understanding of that data? We know that even in our everyday lives now, machine learning can undertake tasks that we would never have believed possible even a few years ago. These are some photographs that I took, actually they took in the Falkland Islands, of some penguins on one of my trips to Antarctica. And you can see that there's a bird that has photobombed my pictures of penguins. And it's trivial now to put into Google or some other search engine, and it can immediately identify which bird it is that has been photobombing your images. And in this case, it's a turkey vulture. But machine learning is even more powerful than that these days. And I can rather trivially use algorithms to remove the photobombing bird. Now, can we use these same sort of machine learning techniques to develop data-driven methods of improving our understanding of an ability to predict future climate? Well, that's something that we've been looking at a lot, merging together both physics-based and data-driven models. So I want to just explain to you a little bit about what we've been doing in terms of some of that work. And this is all work that I've been undertaking with some really excellent students and postdocs in Cambridge. So this graph that you see here shows the distribution in summer, June, July, August, over the period from 1980 to 2019 of temperature in Chicago, the daily average temperature distribution in summer. And there's two plots shown. One is the actual observations, which are shown in blue, and the other is the projections from a model that's been run over the same historical period, one of the climate models. And what you can see is that the climate model does a reasonable job of replicating the actual observed temperatures, but it's biased warm. It's predicted that there would have been more warm, very warm days than there actually were observed to be. And if I'd shown you a different model for the same location, it may well have been biased cold, or if I looked at a different location, it might have been biased warm or cold, but they're never an exact match. And so what we've been looking at is whether or not we can learn that mismatch between the observed, the actual data that we have for a particular location, particularly focused on understanding the more extreme weather events, the bias between that and the models, and use that to apply a bias correction that we can also be applying to the future projections as well. So we can essentially learn a way of producing a better projection into the future that is consistent with past temperatures. And so we've been doing that, and when we do that, we're then able to produce more robust projections of the risk of extreme weather conditions. And this is just one particular result, and you can see all the students and postdocs who've been involved in undertaking this work. This is looking in particular, in this case, at the expected increase in the once a decade extreme temperatures from 2000 to 2040. And you know, all the places in red are places of the world where we expect to see a significant increase in the number of very hot days. So that's one aspect of the climate where we've been using machine learning to try and improve our projections. Another aspect of the climate where we've been doing that is looking at some aspects which are very hard to model. So sea ice is something that is just fundamentally hard to produce a computer simulation of. And that's in part because, whereas I described with the atmosphere and ocean, that they're essentially fluids on a rotating sphere, in terms of sea ice, there's a huge number of physical processes that happen on many different scales that makes it just much harder to model. The Arctic sea ice has been decreasing really dramatically, and you can see at the bottom on the left-hand side here a graph of the extent of Arctic sea ice. There's precipitous decline. This is showing the end of the melt season in September, and today it's about half the extent that it was in 1979, which is the start of the satellite record. And what we've been doing is looking to see whether or not we can, rather than produce try and attempt to produce physics-based projections of future sea ice, instead look to see whether we can produce data-driven projections, taking together information about the current state of sea ice extent and other physical aspects that we know have an impact on the future of that sea ice. So aspects to do with the temperature, to do with the pressure, to do with the wind systems and so forth, and put that together in a data-driven modelling approach to produce future projections. And the map that you see is where we undertook use such a model to produce, with lead times of just a month or so, future projections of the seasonal change in the amount of sea ice. We've also been looking at other aspects of the climate system. Again, how can we start to develop data-driven models, looking at the evolution of ocean models, or looking at whether or not we can use data-driven approaches to reproduce hydrological models. So this is still very much at the forefront of research, but the hope is that by bringing together not only the physics-based models, but now introducing as well these data-driven models, that we will start to push the boundaries of our predictive power yet further. And it's actually very exciting that this is potentially, in many aspects, really an opportunity for transformational change in our ability to make projections. So I want now to turn to how mathematics can be used to help to contribute to sustainable solutions. So I've already shown you how carbon dioxide levels have been increasing dramatically in the atmosphere. The white dots on this graph here show how those carbon dioxide emissions have been changing over the last few decades. 2020 actually a slight dip in the amount of emissions globally as a consequence of the lockdowns that we saw in economies around the world. The blue sort of splodge that you see on this graph here shows the future trajectory of emissions that the climate models that I've just been describing indicate would be necessary if we were to limit temperature increase to 1.5 degrees of warming. And as I described, we're already at just over 1 degree of warming. Dramatic decreases in emissions are required over the next 3 decades. So then globally, we reach net zero emissions by around about the middle of the century. That translates into the need for a radical transformation of our economy and our society. And this is just looking at data from the UK. Each of the squares that you see here show the same amount of emissions coming from different sectors. And you can see what the emissions from the UK looks like in all those different sectors in 1990. There's actually been a significant decrease in emissions over the past 30 years, particularly from the energy sector. Back in 1990, a lot of our electricity was still generated by coal. Today, very, very little is. And that, together with general efficiencies, have reduced significantly our amount of emissions. But there's still a long way to go over the next 30 years if we're to reach net zero emissions, which is what in the UK we are now, is now the goal for the UK. Now, of course, significant innovations do happen. If we look back at 1990 and the telecommunications technologies that were around in 1990 compared to today, when today we're doing everything virtually, and try and imagine the sorts of changes that might happen over the next 30 years, then you can see that, you know, enormous innovation potentials are possible. But where might mathematics and mathematically derived technologies or solutions come to bear? Well, let's look at all those different sectors where we need to see a transformation in each of those different sectors over the next 30 years. And in each of them, there's an opportunity for maths-based solutions to play a critical role in terms of the transformation. So just to give you a few examples, in the energy sector, it's already the case that the development of digital twins, essentially mathematical models of energy systems, are helping to make the running of those energy systems much more efficient. In terms of the transport sector, there are huge opportunities for, again, using mathematical modeling, either to make transportation systems more efficient, or also in terms of our ability to design new modes of transport. And one of the areas of research in Cambridge, which is being undertaken, is a significant effort to look at the development of electric planes, and planes that can be with changes to their aerodynamics that can be significantly more efficient. In terms of agriculture, looking at how we can introduce AI, for example, in terms of making agriculture smarter, using less chemicals in terms of the agricultural systems themselves. Looking at how, again, we might be able to use AI to produce new, to identify new materials that we can use in industrial sectors that currently have significant amounts of emissions, and so forth. Every sector that we look at, there are opportunities for using mathematics in terms of developing solutions to transform those sectors into zero carbon sectors. So I hope that's given you a little bit of an insight into some of the things, both where mathematics can help to improve our understanding of our changing climate, but also help to shape some of the solutions. If you're interested in finding out more about Cambridge Zero, then you can visit our website. If you're interested in finding out some more of the work that we're doing, starting to apply AI and machine learning to understand some of these problems, we have a Centre for Doctoral Training in the application of AI to the study of environmental risks at the university. So please do look at the things we're undertaking there. I also wanted to point out that this evening is Earth Hour, which is a global initiative that's been running for decades now to switch off everyone's lights for an hour as an indication of the need for that transformational change to address climate change. And finally, if you want to ask any questions, there's a link there to the Slido on which you can. So thank you very much.
Emily, that was amazing and interesting. Thank you. So I'll just reiterate what Emily just said about asking questions. So a few are beginning to come in, but if you want to ask a question, you can go to slido.com, and then the code that you need to type in, which has been put on the Eventbrite page and other pages, is 984, then A for alpha and S for sugar. So 984, A for alpha, S for sugar. So, Emily, the first question that has come in is all about machine learning. And I suspect that this might be a question that a few people in our audience have been wondering about. So you talked about training the model. And so the question that came in was, climate models use something called bias correction to make the model agree with real measurements. And then the question is isn't that a fudge? Shouldn't the model get better? So do you want to talk a little bit about training models and things, please?
Yeah, so the physics-based models, so what we're trying to do there is to try to add in our additional information from how the weather has changed in the past to if you like, as an extra set of information that we can include in our future projections. So the climate models themselves, so I mean, you might, in a way it is a fudge, but it's a fudge that's designed to introduce additional information into our projections. So we're just trying to draw on all the sources of information that we have. And some of that sources of information is our understanding of the physics, which is what is being used to create future projections. But what we're additionally trying to add in through the machine learning and what we're calling bias correction is the additional information that at the moment isn't being included, which is that we know how the weather has changed in the past. So we're just trying to use that additional information so that we're using all sources of information that we have to try and better project the future.
So essentially you could think of it as a data training set that you're using.
It's just the data training set that we're using, yeah.
Fantastic. That's really helpful. Thank you. I'm sure that will have really clarified it for lots of people. Thank you. So the next question is a more personal question to ask you how you feel about this. So the question is, are you ever overwhelmed by the scale of the challenge that climate change presents?
Yes. and you know what, especially I mean, as I showed you a couple of photographs from the Falkland Islands of penguins, but I mean, especially when you go to the polar regions, and my former colleagues from the British Antarctic Survey, one of the big projects that they've been undertaking over recent years has been looking at the West Antarctic ice sheet, and in particular one of the glaciers that's critical to the stability of the West Antarctic ice sheet, called the Thwaites Glacier. And there's quite a increasing evidence that that glacier may even be in irreversible retreat, and the real concern is for the stability of that whole West Antarctic ice sheet. And the reason that can sometimes seem overwhelming is because that holds within it many meters of sea level rise, and if it eventually collapsed, the scale of the change is overwhelming. I mean, it would completely transform global coastlines. We don't know how long it would take, but the scale of the changes that are occurring and the implications of those in terms of the polar regions is genuinely frightening.
I was hoping for something more optimistic, Emily.
Well, the optimistic thing, though, I think is the bit Sarah was coming on to at the end, though. The optimistic bit is the opportunities for making genuinely transformational change. And some of that is about technologies, and I described some of those technologies. Some of it is also about looking at how we can work with nature rather than against nature, how we can look to restore some of our damaged landscapes, for example, so that they help both create resilience to climate change, but also help to mitigate climate change by drawing down some of the carbon dioxide and other greenhouse gases from the atmosphere. And again, actually, in terms of that, our ability to be able to model the climate and other natural systems using mathematics is absolutely central to our ability to understand how do we best go in and support nature to do that. So, you can't avoid mathematics in any of this. It's central to all of it.
Fantastic, thank you. So the next question that's come in is, how much of an impact on climate change do you believe the 2030 petrol car ban in London will be?
Yeah, so, well, you saw one of the key sectors that I had on my plots there was the transport sector. And in terms of all of those different sectors, if you look carefully at the different boxes that I had, how much things had changed between 1990 and today, the energy sector, as I described, for the UK has reduced quite significantly in terms of the emissions from the energy sector, but the transport sector and other sectors to date haven't really changed at all. And so absolutely key to reducing emissions in the transport sector is very rapidly moving to electric vehicles for our personal transport. And we, that is starting to be really clear that for most people, the next, if we do buy a car at all, the next car is likely to be an electric car. But it's not just about that, it's also about changing the way that we travel around. And again, I think there's some trends we can see in terms of that already. The pandemic, I think, has shown us that perhaps we don't need to be flying around the world quite as much as we have done previously, certainly not for business. So many more things have been happening virtually than ever before. And I think everyone has realized that actually there's an awful lot that one can achieve virtually rather than having to travel, certainly for academia, for conferences. So maybe some of these changes will happen in terms of us just changing the way we travel as well.
Fantastic, thank you. Okay, so I'm going to carry on. We've got a few more questions and we've got a bit more time. So the next question is, how close do you think we are to hitting a tipping point where it would be impossible to reverse climate change?
Well, so there's quite a number of different potential tipping points in the system. And actually, I keep on coming back to mathematics, but this is another really interesting mathematical question, both whether there are tipping points and whether whether you're close to one or not. Those are both interesting mathematical questions. But some of the potential concerning tipping points, I've already mentioned the risk of collapse of the West Antarctic ice sheet, or similarly in Greenland. There's also concerns about the ice sheet there. There's concerns about the Amazon rainforest, which is a huge sink. It soaks up large quantities of carbon dioxide. We know that it could flip from being a rainforest into more of a savanna, and then that would introduce significantly extra carbon dioxide into the atmosphere and increase that effect. In the Arctic, there are vast stores of frozen methane in the permafrost in the ground, or at the bottom of the ocean, or in lakes. And as the Arctic warms up, the concern is that that methane may be released to the atmosphere. And methane is a much more powerful greenhouse gas than carbon dioxide even. So again, could act as a significant acceleration of the warming. It changes tipping points in terms of changes of the circulation of the oceans is another key concern. And in most of these cases, we know that similar things have happened in the distant past. I showed those ice core records. For example, if you look at the ice core records from Greenland, you can see periods in history where we've seen jumps of 10 degrees Celsius in a decade or so. So there have been periods, we're currently in a period of the Earth's history where the climate is unusually stable. We know that the climate can undergo much more rapid changes, and the concern is that as we increase the temperatures, you increase the risk of flipping into those different climatic states.
Now I've got a lovely, perfect Science Festival question for you, which has just come in, which says, Emily, do you think that school-age children could use climate problems to explore maths, or is the maths needed just too advanced?
No, I think there's all sorts of questions at different levels of school education where climate is a really nice way of being able to understand mathematics and the science more generally. So actually, one of the things that I did early on in the last year when all the schools were, all the school children were at home, I did a whole set of videos with my children, many of which used a lot of mathematics and were aimed at primary school children. And we even did some machine learning so I was interested at the time in looking, one of the videos I did looked at air quality, and we were interested in how air quality had changed as a consequence of nobody traveling so much, not so many cars on the road. And so one of the things involving machine learning that I did was with the children, we used a a way of using machine learning to detect whether or not there was a car or a pedestrian or a bus on the street, trained it in order to do that. And then we were looking at the data sets as well. So there's just one example. People can, I'll post later on Twitter or something, the links to those videos so people can look. But there's all sorts of different ways. And I think that in terms of school education, so many people are really interested in changing climate. It's a really, I think there's a lot of, lot of interest, and therefore it's a really good way of introducing maths and science to school-age children.
And I am completely with you on that, Emily. I think it's really important. And in fact, I think almost every part of our lives, we can build mathematical scenarios into children's learning in everything that we do. So now we're getting a bit more technical again. So another question, how do you expect quantum computing will help address math problems in climate change? Are there any examples?
Yeah, so there's always been a lot of interest in how quantum computing might be able to be used in climate related problems. I mean, projecting future climate is a big computational effort. And so every different new development on the computing side, we're always interested in understanding how we can use that new technology to improve our projections of, or the ways in which we project future climate. So, yes, when the technology is available, then yes, we'll look at ways of using it.
Great, thank you. I might just take a couple more questions because we're almost over time, but so many awesome questions have been coming in. So I will go with this one now. So how is the IPCC, so that's the Intergovernmental Panel on Climate Change, how is it using new research in its predictions?
So the IPCC, it draws on all the published research, so it doesn't do research itself. It's a sort of gathering together that happens every 5 years or so of all the research that's been undertaken and published, and so any new advances in terms of the scientific research then get fed into the latest IPCC reports, and the next report in terms of our understanding of the physics of the climate system is due out this coming summer.
Okay, thank you very much. And I might just ask you one final question. So is it possible to make a model that shows an integrated climate change, not just for the whole country, but for the whole world? Do you want to talk to a little bit about that?
So the climate models do attempt to do produce global projections of the climate system, but the big question is not just how the weather and climate themselves are going to change, but what the knock-on impacts of that are in terms of things that affect our lives, whether that's the knock-on impacts on health or the knock-on effects on different aspects of the economy and so forth. And so creating models or sets of models that enable us to do that is well, that's even more challenging because you start to need to create a model of the whole world. And actually another area that we're interested in looking at using machine learning is to, if you like, couple together the information coming from the climate models in terms of how the climate itself is changing, and then the impacts of that in terms of, for example, health. Because if we can use data-driven approaches to tell us how to link those two things together, then we can start to get projections of what the impacts on health, for example, are. So it's another area that we're really interested in seeing how we can use machine learning in order to give us greater insight.
Fantastic. Thank you so much, Emily. It's been just so interesting and exciting to hear all of this. Thank you so much. And put in such wonderfully clear terms as well. So I think we'd probably better draw to a close now, because that's what we said between 3 and 4. But what I might just say is that lots of people who want to find out more information can go to Cambridge Zero. You've got huge amounts of resources there. Also, I think I was reflecting on the question about work that school children could do, and BBC Bite Size, I think, have some awesome resources on climate change as well. and of course there's your wonderful Ladybird book as well to recommend. So can I just say thank you so much, Emily. We can't wait to welcome you back to the Institute again for real, but this has just been amazing what you've done for us for the Cambridge Festival. So thank you very much, and we look forward to seeing you again soon.
Oh, thank you very much.
Take care. Bye-bye.